So yesterday we talked about the background motivation and definition of Laplace transforms. We computed some examples, some easy examples, and we saw a sufficient criterion for existence, right? So let me recall what this was, because I didn't prove this theorem. So let me prove it today. So theorem. So if ft is a piecewise continuous function for 0 less than t less than equal to t naught, and is of exponential type for t greater than t naught, then what was the conclusion? Sorry? Where is the hypothesis? Exists. Exactly. So then f of s, which is given by the Laplace transform of ft, exists, okay, for which region? S greater than alpha. And what was this alpha? This is the exponential order, right? Alpha is the exponential order of f. So does everybody remember what was the exponential order? Sorry? Yeah, so modulus of f of t is less than equal to m times minus alpha t, right? So this is for t greater than equal to t naught, okay? So I'm implicitly assuming that I'm working on the positive real axis, okay? Very good. So let's prove this. Proof. So how can we prove it? Any ideas? So we just start with basic, yeah? Trying to write out what is fs. Fs equals 0 to infinity ft to the minus st dt. This is our formula for the Laplace transform. Now I want to prove that this exists for s greater than alpha when ft is of exponential order alpha. So here we have a t naught for which ft is piecewise continuous, okay? So let's, yeah, perfect. So let's break up this integral from 0 to t naught and then t naught to infinity. And we look at this term separately. Okay. So this is a definite integral. Let me call it I1 and let me call this I2. So because ft is piecewise continuous in this region 0 to t naught, this integral exists. This is a fact of Riemann integration. Okay. So since ft is piecewise continuous for 0 less than equal to t less than equal to t naught, then I1 is finite. Okay, this is a fact of Riemann integration from Riemann integration theory. Okay, so we are left to deal with I2, and this is the part where we have to use the exponential order. So according to our hypothesis in this theorem, ft has exponential order for t greater than t naught. So in this region from t naught to infinity, ft has exponential order. So we want to estimate the modulus of I2. Okay, so this is the modulus. So t naught to infinity ft exponential minus st dt, and this is less than or equal to t naught to infinity modulus of ft st dt. Is this clear? Okay, and here is where we use the exponential order part. So in this region, in the region t naught to infinity, ft has exponential order alpha. So modulus of ft e to the minus st is less than or equal to what? M times e to the minus s minus alpha t, right? So here, if s is greater than alpha, this is positive. Okay, s minus alpha is positive, and that's why this integrand will become integrable. Okay, so the thing inside the integral will make sense. So this is less than or equal to, so I come here, integral t naught to infinity m e to the minus s minus alpha t dt. Note that I am no longer putting the absolute value here because it's already positive. Okay, and what is this? So you can just integrate this part. You can take m outside the integral. So this is e to the s minus alpha t over minus s minus alpha, and the limits of integration are from t naught to infinity. Right? So, what do we get? Sorry? At t naught? At infinity it's 0 for this region. If s is greater than alpha, then this is positive, and when t goes to infinity, the whole thing is negative. E to the minus infinity is 0. So this is m0 minus exponential minus s minus alpha t naught over minus s minus alpha. So there is a plus sign. So this is just m exponential minus s minus alpha t naught over s minus alpha. So as long as s minus alpha is positive, so here you cannot take s to be alpha also. It has to be greater than alpha. This is this integration is well defined. Okay. So here then this part is finite, and we have proved that this part is also finite. Okay. So let me write it here. So the final conclusion is that Fs 0 to infinity Ft minus St dt exists for s greater than alpha. Is this clear? Any doubts about this proof? No questions? Okay, good. Okay. Are there any doubts? By the way, yesterday there were some questions about functions of exponential order. Right? Yes. So can we prove it? How to prove it? Okay. So yesterday I claim Ft equals t to the n greater than 0 is of exponential type with some exponential order that we have to find out. So what do we have to prove? We have to prove that modulus of t to the n exponential minus, or let me put it on the other side. So we have to prove that there exists, everybody knows this symbol? There exists t naught positive such that modulus of t to the power n, also there should exist m and m greater than 0 and alpha greater than 0, okay, such that modulus of t to the power n is less than or equal to m into the plus alpha t for all t greater than t naught. So we have to find three things. We have to find t naught, m, and alpha. Okay. So let's see how. So what can we do? So the first observation is that if t is greater than 0, this is already positive, so you can forget about the modulus. right? Isn't it? Modulus of t to the power n is t to the power n for t positive. Is this true? Everyone agrees? Okay. So this thing, this inequality is equivalent to proving t to the power n is less than or equal to m e to the alpha t for some values of m alpha and t naught. So what can we do about this inequality? Sorry? Expand. In what? You want to use the series, is it? Okay.
You can divide by the right hand side and take limit t tends to infinity, get the limit 0.
Why? That's what we are trying to prove actually. That is what we are trying to prove exactly, that when you take t to the n e to the minus alpha t and you let t to the t goes to infinity, then it's 0. So one thing you can do, as she said, that you can expand it in power series. Okay. The other thing you can do is just take logarithms. Okay. Everything is positive, so there is no problem. So what do you get when you take logarithm? N log t. And here? Sorry? Log m plus alpha t. Right? And is it true that if t to the n is less than or equal to m to the e alpha t, then you can put less than or equal to here? Is this true? Yes. Log is a monotonically increasing function. Okay? In fact, this is equivalent. Okay? So, now what can we do? Any ideas? So what is going on actually here? So let's see in a graph. So here log t on the right hand side, and you have 1 over n log m plus alpha over n t. Okay? So what does the graph of log t look like? Or let me draw it on the other side. So this is, let's say, x, this is y equals x. And what is the graph of log t look like? Near 0 it is minus infinity. So it goes like this. And it converges asymptotically to y equals x, right? So in fact, if alpha by n is greater than 1, right, and if this is positive, okay, then so you can write log t is less than t. This is always true for t positive, right? But t will be less than alpha by n t plus 1 over n log m if what? If this is positive and this is greater than 1. Does everyone agree? So let me do it step by step. If alpha is greater than n. Do you agree? T is less than alpha by n t if alpha is greater than n. Right? You're just multiplying by something which is greater than 1. So it has to be greater than t. Okay. Then I can add anything positive and it will still be less than equal. Right? So in the end you get log t is less than alpha by n t plus 1 by n log m, but you need this part to be positive also. Okay. So we have two conditions: if alpha greater than n and 1 by n log m is positive, but this is just saying that log m is positive, which is just saying that log m, m is greater than 1. Okay. And in fact, this will be valid for all t greater than 0. So t naught is in fact 0. Okay. So for all t greater than 0. Does everyone agree with this proof? So we have found in the end m, alpha and t naught such that t to the power n is less than or equal to m e to the power alpha t. Is it clear? You asked the question. Is it okay? No problems with the arguments? Okay. You, not everybody seems convinced with this argument, right? So what is the problem? Tell me. So we want to prove this one. Okay, we have converted the original statement into a statement about logarithms by taking logs on both sides. Okay, that was the first step. And then we just manipulate this inequality. Okay, because n is positive, we can divide by n. Okay, and on the left hand side you're left with just log t, and on the right hand side you have some expression of alpha, m, n and t, and you have to find the right of values of alpha, m and t for which this inequality holds. Okay. So I did this in 2 steps, actually 3 steps. First I said that log t is less than t for t positive. Okay. Then I said that t is less than alpha by nt when alpha is greater than n. Okay. Then I added a positive term log m by n. Okay, and said that this thing is less than this thing plus something positive, which is a redundant statement, right? Okay. So what are the values of alpha and m for which this inequality holds? I said that alpha should be greater than n, so that this is greater than 1, right? For which this inequality holds. And for the second inequality, third inequality, I wanted that log m should be greater than 0, right? And what is the value for which log m is greater than 0? M being greater than 1. Okay. So this is what I wrote down. So for every t positive, alpha greater than n and m greater than 1, this inequality holds. So on the left hand side you have log t, it's just the same inequality here. Okay. This is what we proved. Is it clear? Okay. The second thing is that every bounded function, bounded continuous function. So second claim, so let me call this 1. Two, every bounded continuous function on the positive real line is of exponential type. Okay, I leave it as an exercise. Just think about it, why it should be true. Try to argue maybe similar to what I did. So I leave this as an exercise. And maybe we can, if it's not clear, then we can try to solve it in the tutorial class tomorrow. Sorry, tutorial class is today, right? Ah, sorry. Okay. So now let's look at some basic properties of Laplace transforms. Okay. Basic properties of Laplace transform. Okay. So first thing to do is check about linearity property. So what is the linearity property? So suppose ft and gt have Laplace transforms Fs and Gs. Okay. Then for any constants alpha beta, so alpha and beta can be real or complex. What can we say? The Laplace transform of alpha ft plus beta gt is equal to, what is it? Alpha fs plus beta gs. Okay. Is it true for all values of s? Sorry? S positive. Why do you say that? S is right. So you have to be careful, because Fs, in fact, forget about the sum. Fs might not be defined for S positive, like we saw in the proof of exponential order. You saw that Fs was only defined for S greater than alpha. Okay, and alpha can vary anywhere. Okay. So suppose that Fs is defined for, so this is not the same alpha, so I should maybe remove C1 and C2. C1, C2, C1, C2. So if f, this small f, is of exponential order alpha, then this is defined for s greater than alpha. If gt has exponential order beta, then gs, capital Gs, the Laplace transform, is defined for s greater than beta, right? Then what can you say about the sum? When is it defined? So exactly. So you have to be a bit careful. You can definitely say that C1 Fs plus C2 Gs is defined in the common region of convergence. Does everybody remember this terminology? Region of convergence? I wrote down yesterday. So the region of convergence is the set of values of S for which the Laplace transforms are defined. So here, for example, if S is greater than if Fs is defined for S greater than alpha and Gs is defined for S greater than beta, this whole thing will be defined for S greater than maximum of alpha beta. Is it clear? Okay. So what I would like to emphasize is that whenever you write down a Laplace transform, it is very important to also write down the region of convergence. Otherwise, things can go horribly wrong. Okay. Okay. One remark I would like to make. So here, this is a sum, Laplace transform of sums. What about Laplace transform of products? So suppose that ft and gt have Laplace transform fs and gs, then is it true that the Laplace transform of ft gt is equal to fs gs for all functions f and g? Sorry?
It depends on how do we define product.
It's just the usual product. ft is a real number, gt is a real number, right? So the product is just pointwise product. Okay. So f dot g of t is just ft gt. You're right that you have to be careful in defining the product. But let's just say that the product is defined pointwise. Then is it true that the limit of the Laplace transform of ft gt is given by the product of the Laplace transforms? No? Yes? Sorry? It's not possible at all? Or is it possible for some f and g and not possible for some other f and g, or is it not possible for any f and g? Possible for all f and g? Huh? If one of the functions is constant, then it's perfect. So we have found some f and g for which this is true, but it's not true in general. Can we give a counter example? So whenever you want to say that no, this is not true in general, we want to give a counter example. So what is the counter example? So find f g such that L of f t gt is not equal to L of f t L of gt. Both are?
GFT1.
Okay. Then what is the left hand side?
Left-hand side
Very good,
L of-
yes.
L of 1 by
F of t, GFT is 1, right?
L of 1 equal to 1 by
So L of 1 is
1 by S.
1 by S.
Right hand side L of 1 into L of 1
Right,
by S square.
right. On the right hand side, so this is not true. Very good example.
So can you prove the existence of Laplace transform of product if the Laplace transform exists for f of t and g of t?
This is a good question. Have you thought about it? And how can you find conditions under which this is true? I don't know of any general conditions for which this is true. This is a good question. I don't know the answer to this. Okay. But all we are saying at this moment is that it's not true in general, right? Okay, so this is the linearity property. We didn't prove it, right? Can we write down a proof? What is the proof? Any ideas? Why should it be true? Exactly. Very good. So let's just write f t plus c2 gt. This is what? Integral of 0 to infinity c1 ft plus c2 gt. And first you use, what is the law for which you can take, you can write it as c1 ft e to the minus t plus c2 gt e to the minus st. Under which law is this true? So these are all real numbers, right? Suppose C1, C2, everything is real. Distributive law, exactly. This is the distributive law for real numbers. Real or complex numbers, okay? And then you can use the linearity property, like I said, linearity property of integrals. So this is a silly question, I agree. Why should this be true? But in mathematics, one has to be able to give an answer whenever you write down something. And if somebody asks, why did you write this down? You have to be able to give the answer. Okay? That's why mathematics is said to be a rigorous process. You have to have a rigorous method of analysis. Rigorous means that you have to be able to justify your calculations. In physics, this is not true. Very good. So the next property is called, this is the first shifting property. What is this? So if L of ft, so fs is L of ft. S greater than 0 exists, then for any constant C, this is real or complex, the Laplace transform of exponential Ct ft, what is this? F of S minus C. What is the region of convergence? Sorry? S greater than? Okay. You have to be careful here, okay? If C is real, S is real, then it's okay. No problem. But remember that we have defined it for S positive, but if C is a complex number, then S should be greater than the real part of C. Okay? Because if you just write S greater than C, it does not make any sense because C is a complex number, S is a real number. Okay? So this should be true. Okay, proof. This is a very easy proof. So let's write L of exponential Ct ft is equal to 0 to infinity e to the Ct ft e to the minus st dt, 0 to infinity ft e to the minus s minus c t dt, and this is f of s minus c. Okay. So this is for s greater than real part of c. Why do I need s greater than real part of c?
This function, suppose we consider f is one constant and g is any
In this counter example, yes, tell me.
suppose we consider f is constant.
F is constant. Yes.
G is any function.
Okay.
That time also we cannot find it.
Yes. Yes.
Product is not always.
Yeah. So it's for many functions. This is not true. This property does not hold for many functions. Okay. I mean, you can. What I mean by that is that you can find many examples or counter examples where this does not hold.
Can we find any one function?
Yes. Someone just said, if you just take f and g constant. Sorry. Sorry. Yeah. Constant won't work. If you take g equals 0 and f to be anything, then it has to work, right? So this is a trivial example where this holds, but I really don't know of any non-trivial examples where this holds. Okay. Non-trivial. That's what I'm saying. I cannot remember any non-trivial examples where this holds. Okay. Let me think about it, and maybe I can come up with something. But I think it's not true in general. So yeah, what I was saying here is, why do we need s greater than real part of c? So suppose that I put here alpha, okay, where alpha is the exponential order of ft, then what should be the condition here? should be alpha plus real part of c. And you need this if you try to do the computation with the exponential order like I did in the proof of the existence, then you will see that this integral converges only for these values, because you write it down. So you have ft e to the minus s minus c t. If c is a complex number, so let's take c to be c1 plus c2i. Okay, this is a complex number. Then this is ft e to the minus c s minus c1 minus ic2 t. Okay? But when you take the modulus of this, what is this? Exponential s minus c1 t exponential. And what's the modulus of this? 1. So this goes away. Okay? And you want this to be positive for the integral to converge, right? This is why the real part of c enters there. Okay? Okay. Second shifting property. So let Fs is the Laplace transform of some function t for some region of convergence, let's say S positive. Then define Gt to be f of t minus a for t greater than a and 0 for t less than a for some a greater than 0. Okay? Then the Laplace transform of Gt is anyone? E to the minus as fs fs. Right? This is the second shifting property. So you see that multiplying with an exponential function on the input side, you get a translation function on the output side. And if you translate the function on the input side, you get a multiplication by e to the minus as on the output side. Okay? So there is some duality that plays out in Laplace transforms. Okay. Can we prove this? This is also quite easy. Proof. So what is the Laplace transform of Gt? This is 0 to infinity Gt e to the minus st dt. What is this? If you can break it up, 0 to a Gt to the minus st dt plus a to infinity gt dt. What is the value of gt in this interval? It is 0, right? If t is less than a, it's 0. Note that I did not put less than equal to, but it will not change the value of the integral. Okay. This is 0 plus a to infinity. What is the value of gt in this region? It's f of t minus a. Now we do a change of variables, right? So let's write u equals t minus a. So du equals dt, right? And what do you get? You get 0 to infinity. When t is a, u is 0. When t is infinity, u is infinity. So you get 0 to infinity f of u e to the minus s u plus a, right? Then this is equal to, now exponential minus s a is constant in this integral, so it will come out this exponential minus as or sa, and what you are left with is the Laplace transform of f. Okay. So this is the second shifting theorem. So it's time. So we have only 5 minutes. Are there any questions up till now? Because in the tutorial then we will discuss examples. No questions? So what is the region of convergence? I didn't write it down. What is the region of convergence for GS? Anyone? Fs is defined for S positive, right? Then what is the region of convergence for GS is the question. It's the same, right? So there is no problem in this region. You only need Fs to be defined. This is already defined in this region. Okay. So GS is well defined wherever Fs is well defined. Right? Okay. I'll do one more quickly. This is called change of scale property. What's the change of scale property? If Fs is the Laplace transform of Ft for S positive and A is a non-zero constant, then the Laplace transform of f of At, what is this? 1 by A capital F of S by A. Sorry? Mod A. One by mod A. So let's prove this. So what is L of f of at? This is equal to integral f of at e to the minus st dt 0 to infinity. Okay. So we do again a change of variables at. So du equals a dt, and if a is not equal to 0, then when t is 0, u is 0, and when t is infinity, u is infinity. So you have the same limits of integration. So 0 to infinity f of u exponential minus s. What's t? It's u by a du. Du is a dt, right? So du is okay. So this is 1 over a 0 to infinity f u e to the minus s over a u du, and what is this? F of s by a. So in fact there is no modulus. So it was correct. This is okay. Sorry? A is positive. Yeah. This is very, yes. You are absolutely right. A should be positive. Yes. So A is constant. So again, because if A is negative, then we will have problems with convergence. Okay? Yes. Thank you. Okay, so I think we are out of time today. Are there any questions?
Is this transformation is one?
Yes.
Is this Laplace transform?
Yeah. Is it 1, 1? No. It depends on what kind of functions you are looking at. Okay, so we will do inverse when you are doing inverse Laplace transform. We will learn that in fact two functions can have the same Laplace transform, but they will differ only at isolated values. So there will not be in an interval of positive length where the functions will differ. Okay, they will only differ at isolated values of the real line, of the positive real line. Okay, we will do it when we study inverse Laplace transform. If you are restricting to continuous functions, okay, only continuous functions of exponential order, then it is 1 to 1. Okay, we will see later how that